Hello students. Now the transient response of block diagrams, the lecture continues. Now in this lecture what we're going to do is, like in the previous case, we have taken this block diagram where we are studying the response of change in the input variable with respect to the output by using different controllers. We're trying to find out the offset. Now in the previous case we have taken a proportional controller and we calculated the offset for the servo problem as well as for the regulatory problem. Clear? Now in this in the second case, what we're going to consider is, we're going to take now the case of the proportional controller and we're going to find out the offset for the servo problem. Clearly, now further what you can do is, you can find out the offset for the regulatory problem on your own. Over here I'll solve the case for the servo problem. Now for servo case, let's use the same block diagram. We have TR dash over here, that's the case, the controller, servo proportional control, we use proportional controller, that is KC in the last case. Now we have using proportional integral, so it will be 1 plus 1 upon tau is. The final controlling element was ignored. We have tau I over here. Obviously there is a block over here, but for the servo case let's ignore that part. WC over tau s plus 1, that is T, and measuring element was also ignored. The dynamics of measuring element was also ignored. Now for servo problem, the load distribution is set to 0, so this term is set equal to 0. Then we're going to find out T by T dash R. Now for simplicity, the values of Kc is taken as 1, the value of tau I is also taken as 1. These are the two parameter values which can be changed according to the stability, but for the simplicity over here we are taking them to be a 1 1. So the block, let's find out the overall transfer function, that is T by Tr dash. So for that, our block diagram looks something like this. We have S plus 1 over S, because Kc is 1, tau is 1, this can be rearranged, becomes S plus 1 over S, and that's 1. Okay, 1 by Wc can be taken as A, so we have A upon tau s plus 1. This goes, we have a negative feed backward, again the same case, and T, so we have T dash R. So T by Tr dash will come out to be S plus 1 into A upon tau s square plus A plus 1 S plus A. I have solved it and this is my transfer function. Clear? Now you can solve this block diagram because they are in series, and then the main loop is in the forward, and then we have a feedback which is going in the backward direction. So you can use the rule of the block diagram reduction and you have this transfer function. Now if set point is given a unit step change, for a unit step change, that is Tr dash is 1 by S, so what will be the change in T? So T becomes 1 by S of S plus 1 into A upon tau s square plus A plus 1 S plus A. Clear? So this can be solved and we can have our T dash T, that variable. But in order to calculate the offset, what we need is T dash R at infinity and T dash at infinity. Clear? Now T dash R at infinity is 1 because it's given a set change of unit step change, so T dash R at infinity is 1. But in order to solve this, we need a partial fraction, and then we can find out T dash T. But we don't require this expression. That expression is only when we need to plot your response with time. Clear? But for the timing, for the offset, we know how do we calculate t dash infinity. How do we calculate this t dash infinity? Now we can use a final value theorem over here to calculate your t dash infinity. Now final value theorem says limit t dash infinity, t approaches infinity, will be nothing but limit s approaches 0, s times t dash s. So t dash s is this part, multiply by s and then put s equal to 0. So do it. So s times t dash s becomes s plus 1 over a over tau s square plus a plus 1 s plus a, putting limit s approaches 0. So s approaches 0, this becomes 0, 0, 0, a by a, it becomes 1. So t dash infinity is 1. So this is also 1. So offset is 1 minus 1, 0. So offset is 0. That means for if we are using PI diagram, if we are using PI controller system, the response, let's say this is the response of t dash r, that is 1, and that's the response of the, which is over here. So that means it fine. Okay, let me, because we're showing a big difference, so let me try to plot it again. So that is your t dash. So you clearly see the offset is 0, it's eliminated. Clear? So whenever we use proportional integral, remember this, offset is eliminated, but there can be what, oscillations depending upon zeta. Now where is zeta over here? If you see the denominator part, that's a second order system, so we can calculate zeta over here. Now for zeta, we know that in the denominator part we have, the denominator part is tau s square plus a plus 1 s plus a, that's the denominator part. But for denominator part we need to get 1 over here, so dividing by a, so it becomes tau by a s square, so a plus 1 over a into s plus 1. So this is your tau square, this is your 2 zeta tau, and from here you can find out the value of zeta. So if zeta is less than 1, so obviously there will be oscillations in the system, and if zeta is equal to 1 or greater than 1, that will be shown by this red line. Clear? But the main aim is of using proportional integral is it eliminates the offset, and oscillations will be because of the nature of this transfer function. Clear? So this is how we can use proportional integral to eliminate the offset. Now for regulatory problem you can try the same case at your places. Again the output will be the offset for using PI controller for regulatory problem will also be 0. Clear? You can try that, practice at your place and let me know. Now moving further, let's take few examples and try to solve those examples, few numerical problems basically. Now over here, let me write it down, the question first. The question is, we are given it's a numerical problem. We have given a control system where we are using a proportional controller Kc of 1.6, and the transfer function of the process is given, which is a second order with a transfer function 5 over s plus 1 into 2s plus 1. That's the output R. C is the output and R is the input, and it's a feedback, that is this. Now what we need to do is, for a step change of 0.1 in R, determine a maximum value of C t and the time at which it occurs. Part B, we need to find out the offset. Part C, and we need to sketch the response. Clear? Now in this case, what we're going to do is, it's a simple case. We'll find out C by R first. So what will be C by R in this case? C by R will be multiply of both these blocks because they are series, and then we have a feed backward. So C by R comes out to be 5 kc upon s plus 1 into 2s plus 1 plus 5 kc. That's my overall transfer function of the block, that is C by R. Now using the kc as 1.6, so this comes out to be 8 upon 2s square plus 3s plus 9. Clear? Again I can write it down in the standard form, the denominator. So we have 8 by 9 upon 2 by 9 s square plus 3 by 9 s plus 1, and that is C by R s. Now we are given a step input of magnitude 0.1, so Cs will be 0.1 over s into 8 by 9 of 2 by 9 s square plus 3 by 9 s plus 1. So we can find out Ct. Now in order to find out Ct, we know this is the second order system. For second order system, let's find out zeta first. So tau square is 2 by 9, so tau comes out to be 0.47, and 2 zeta tau is 1 by 3, so zeta in this case comes out to be 0.353, less than 1. So for underdamped, so less than 1, the response is underdamped. For step input, we have the expression for the underdamped system, that is, so Ct comes out to be 0.1 into 8 by 9 of 1 minus e minus zeta t by tau over under root of 1 minus zeta square sine of 1 minus zeta square t by tau plus phi, where phi is tan inverse under root of 1 minus zeta square by zeta. Clear? So this is the response for the underdamped. Substituting the value of zeta and tau, so we have the expression for Ct. So Ct comes out to be somewhat 0.0889, because we can solve this. So we can solve this 0.1 into this, so it becomes this much into 1 minus 1.068 exponential of minus 0.75 t into sine of 1.98 t plus 69.33 degrees Celsius. So that is this. Now for ultimate value, that is Ct at t equal to infinity, so we can put t equal to infinity, so this becomes 0.0889. Now what is offset? Offset is R infinity minus C infinity. Now what is R infinity? 0.1. C infinity 0.0889. So offset comes out to be 0.0111. So we have calculated the offset. So offset is 0.0111. Now sketch the response. We know that this is a underdamped system, So the response will be somewhat, that's the response, and the ultimate value will be how much? That is this thing, 0.0889. so that's the response versus time. Then comes the maximum value. So we have plotted the response also. Now maximum value of CT, where does the maximum value of CT occurs? Maximum value of CT, if you see the plot, will occur over here, that is somewhere here. And so we can calculate the overshoot, because maximum value is nothing but A by B, A plus B, or A by B is your overshoot, and overshoot is exponential of minus pi zeta over under root of 1 minus zeta square. Zeta we have calculated, so we can calculate overshoot. So overshoot comes out to be, in this case overshoot comes out to be 0.305. so A by B is 0.305, and B we already know that B is 0.0889. so B we already know it's 0.0889, so we can calculate A. So A comes out to be 0.02711, because once this B gets multiplied by 0.305, so we have A. So maximum value will be A plus B, which comes out to be 0.116. so we have the maximum value of CT, which is 0.116. Now time at which it occurs, for that we have the expression for CT, that is this thing. In this expression, put CT as your 0.116, put CT as 0.116. so by iterating different values of t, you have left hand side equal to right hand side. From there you can calculate your maximum value of t. Clear? So upon iterating, your t comes out to be, so upon iterating t comes out to be 1.6 seconds. So maximum value is 0.116. So from the response we can see maximum value will occur at t occur to 1.6, that is at t equal to 1.6, the maximum value will occur. Clear? So this is how we solve different problems, where we can calculate the maximum value, where we can calculate the offset, and where we can sketch the responses. Now you can clearly see we use controller, so we have the offset. If we use proportional integral controller, then the offset would have been eliminated. Clear? So we can solve further more problems which are given in the book. So kindly refer to those problems and try to solve it. So if you have any problem related to solving the offset for any block diagram, you are most welcome to contact me. We can discuss that particular question. Thank you.